Right, so let's roll this one. In this one, we are going to design, in this video, we are going to design the payload system, or the payload structure, in other words. So remember again, if you know it's your first time watching this video, we are designing a CubeSat that can be able to do Earth observation as a mission. So in this case, we need a camera, right? But remember again, since I'm using commercial off-the-shelf systems or components, it means that any device, any component I choose, I will not be radiation hardened. So I'm choosing very cheap components. If, like, someone might ask why, if that camera will even work in space. So my goal is not really to go to space at this point, is to prove is a proof of concept that this thing can be built using like cheap materials. So I've come up with a block diagram for the payload structure, as you can see here, and it's a very basic design, but basically the heart of the system is going to be this camera right here. That camera is connected to an STM32 MCU with power supply, of course, supplying both the camera and the STM32 devices. And then we have an LDO enable control pin here. This LDO enable control pin or connection will provide us with the ability to activate or deactivate the payload, right, from the onboard computer. So if we are not on a mission to capture any image, we can easily turn off and on the system or the camera, right? So the way I intend this to be is, instead of having this payload as like another 100 by 100 by 100 millimeter board, I want it to be like a daughter board that can be mounted on the OBC. So it's smaller in size. It's not following the size structure of the standard CubeSat. You can see here I have put M3 screws or mounting holes so that I am able to mount this payload structure on the OBC. And then here I have put the JST connector header. JST connectors are highly discouraged in like high vibration environments, but for this case I want to see whether at least this structure will work. So this JST header will route all the signals or all the data from the camera module to the OBC or the motherboard, which is going to be the OBC anyway, right? Also, I've put other miscellaneous things like the temperature sensor, obviously, to know the sensor board temperature of your to sense the board temperature of your payload, and a basic user LED here to just probe that the thing is working fine, because we have an STM32 here and whatnot. So how am I going to program this board? So I want it to be programmed from the motherboard, right? I want to share the SWD debug pins. So I will put a toggle switch on the motherboard that can help me to load the program either to the OBC or to the payload STM32 right here. That way I reduce the footprint size of the payload PCB, and the cost, though is not like very significant, but I think it's more of a centralized design that way. Yeah, so that's about it. So basically what I've chosen based on these devices is that the payload is designed using this STM32 F407 VTG with 4 reasons I'll explain in a few seconds. And this is the block diagram for the camera payload. So we have the STM32 F4 VGT6. I've chosen this and based on the research and the capability of the MCU for 2 reasons. Number one, it has what we call the digital camera interface. I'll show you that in the datasheet in a few seconds. So this digital camera interface allows us to communicate with CMOS sensors, obviously the camera, right, through 8-bit parallel or 16-bit parallel. So this this camera is using an 8-bit parallel bus for that. And also you can see that we have the clock synchronization and href pins on this multimedia interface. The other thing is that how do we prove that this camera is working? So I will put an LCD for testing purposes, not on the CubeSat, so that I can see what the video is broadcasting, right? I mean what the camera is broadcasting anyway. Yeah, so we have what we call the static memory controller, right? Static memory controller is used majorly with like devices or components that consume a lot of RAM, especially from the MCU. So the internal RAM for this one is not like enough to handle like high data rates for the LCD, so it has a dedicated hardware accelerator for the static memory, right? And obviously we'll store these pictures or snapshots on the SD card, but this SD card, you see that is using SPI. I don't want to put the SD card on the payload. I want the SD card is put on the OBC. So these signals, the MOSI, MISO, etc., will be routed to the OBC. I realized I have clock and SEK here. It should be CS and then SEK. I'll correct that. So the data will be routed to the MCU or the OBC motherboard. Right, so let's get into it and design that payload on the schematic. Right, okay. The first thing we do obviously is to open the EDA. I've created a new schematic or page here that has the payload, and as usual we go to our LCSC. I think I have searched for this MCU already, so you can see it's not very well, it's not very expensive. Also it's $4 for one part. So I'm gonna copy this part number, come back here, Shift F, paste, place that. And it's also in stock, so it's not really, it's all good, right? So I place 2, that should be 1. Okay, so let's see what happens with this one. Now the data sheet is right here. I think I've opened it, and again, one thing that I will mention is that these STM32 chips share a lot of design features or characteristics. Even if you go through the data sheet, you'll realize that most of the things are the same. So what I'm going to do to accelerate this design is to copy some parts of the OBC to that payload design. So for example, I'll copy this LDO and the decoupling capacitors, right? So this way I ensure that the components are like standardized across the schematic sheets or schematic pages, and it's easier to reduce the time that it takes to design this. So basically we take 5 volts here and pass it through a regulator to get at 3.3 volts. Now you remember that I said I'm gonna have like a LDO control pin. So this is the control pin, this one. So if you tie it high, you activate the LDO regulator. So what I'm gonna do is I'm going to give it a net name and say this is LDO EN. I don't think that's gonna fit. Okay, LDO EN. Let's move this a little bit and this a little bit. Cool. So we can control this automatically. Pull it high to activate, pull it low to deactivate. Cool. So this is 3v3 and I'm gonna connect this 3v3 to this chip. Obviously uses, I've gone through the datasheet a little, it uses 3v3 volts. I'm gonna connect that there. Decoupled VSS is ground, so just gonna put ground here. ground should be pointing downward, but for now I just put it there. I'll like beautify it. I'll beautify this thing later. So what I like to do is copy that and check all the pins that are VSS. So we have one. This is analog reference ground. I'm not going to be using a lot of analog, so I can ground it. There are better ways to do that if you are like using dedicated or external analog stuff. VDD, there's another one. Okay, so just gonna route that, connect that and connect that to ground, right? Okay, so VDD is right there. I'm gonna connect that to 3v3. So okay, let's see, 3v3. Okay, cool. And then VSS, there's another VSS here. VSS right about there. Wire this VDD. I'm gonna put it right there. VDD. Put it there. Next is another VDD. Okay, so that's that. Next is okay, we have VSS VBut. Let's check the datasheet. Datasheet is right here. So look for VBut. So VBut is majorly used to supply RTC, but we can tie that to like we can tie that to 3v3. Okay, so power supply schemes VBut 1.6 to 3.6 volts. You can power it externally, obviously, but since I'm not using RTC in this payload, I can. So you see here, external 32 kilohertz oscillator and backup registers through power switch when VDD is not present. So I'm gonna tie that to VBut somewhere around here. Yep. Okay, next is so we have powered this thing up. Oops. Okay, VSS powered VDD. There's another one here. There's another pair here, VDD and VSS. So I'm just gonna route that there, route that. Okay. Cool. So let's see. Okay. Next, since we have powered the MCU, we need a clock, right? We need to clock it. So I'm gonna search for clock and startup. So on reset, the 16 megahertz internal, this is internal RC is selected as the default, right? So the application can select the system clock either as the RC or an external 426, right? So can be monitored for failure, etc. Frequency can be increased up to 168. Okay, cool. Okay, pretty standard stuff. So we come back here. I think I have a 16 megahertz crystal. Again, I'm gonna take it from here, copy that, I want to remove these two, copy. Okay, I just want to put it right somewhere here. I mean, this can look better, but for now let's deal with that. So I'm gonna like connect this way and that way, just make it a little bit shorter like that. Yep, that way. Okay, So HSC oscillator in, oscillator out, 16 megahertz. So which pins are those? We need to check that. So to help me with this, let me open the STM32 Q by D. It will be very helpful in this case. But I think it's labeled or what? It's not labeled. Clock. Is it labeled really? Should be. It's not labeled. No, it's not labeled. VDDA should be 3.3 or an external voltage that you're using. But I'll just connect it that way. What about this VREF plus? VREF plus reference voltage. Let's see. Okay, so 12-bit, this is mostly for DC stuff. Minimum 1.8, maximum VDDA. So whatever is supplied at VDDA is what the VREF gets. Okay. Power supply decoupling should be performed as shown, depending on whether VREF plus is connected to VDDA or not. Okay, so if it's connected, the 10 and F should be ceramic. Okay, should place them as close to the chip. All right, cool. So VREF is right here, VREF minus, VREF plus is here. If it's connected, we should decouple it. We should decouple this from VDDA through a 10 and F to ground, right? Okay, so power supply, this is the one I want, and reference decoupling when VREF plus is connected to VDDA. So this is coupled 10 and F. So I don't think I have a 10 and F here. Do I have a 10 and F anywhere? Let me search for this 10 and F. I think that. Let's see. Find all ADCU. Okay. Cool. So it's in the ADCU. Cool. It's right here. I'll copy that. Bring it back here. It was from what? VREF plus to ground to VSSA. VREF plus right here. So I'm just gonna connect that there. Ground obviously, so connect that like that. Okay. Temperature says okay. Let's look. Let's see whether we have any other information that we can use. Up. Okay. Right. So okay, let's connect this VREF plus to 3v3 to whatever VDDA is. Right now I'm just connecting them. Don't worry about this monster right here. This is very dirty and cluttered, but yeah, I'll clean it up later. Okay, so we were opening the Q by D to see which pins are used as the what clock, right? So what I'm gonna do is create new project, new STM32 project. Just to download these files. Meanwhile, I can go ahead. I'll put it aside a little here. Let's see. So this thing is like very generic. Like you have the power, which you have done. You have the clock. You have the debug. We have the programming, which is also called debug anyway. But so programmer, I can debug it with UART, right? So let me say this is UART. Oops, what did I do? Okay, let's see. Okay, so STM32 F407 32 F407 F407 what? VGT6 not that one, this one. Just confirm, click that, next. So I'm gonna call it payload shadow flight payload. Save it in the repo. So I'm gonna open this payload firmware and create a new folder here and call it the same name as the this way, like the way Eclipse creates its project, I don't understand this thing. Payload. Okay, so we save it in this folder. This is shadow. C, we use C, finish. Right. So for now, I'm just gonna use it for pinout, but when we write the firmware, we are going to initialize a lot of other stuff like RTOS, middlewares, FATFS, etc. Yeah, license accept. Okay, I'm gonna put this a little bit aside. So we were listing out the parts we need to write. So debug, programmer, we need like a user LED, we need reset and boot. Yeah, just start to get the chip working. Just blink that LED. That should be enough, right? So boot 0 is pulled high when you want to program. So I'm gonna search for it here just to like confirm that functionality. Boot 0. Okay. Let's see. What else can we search? Like startup, boot modes. Yeah, so boot modes. Alright, so a startup boot mode. Boot pins are used to select one of the 3 boot options: user flash, embedded SRAM, system memory. The bootloader is connected in system memory. It is used to program. Okay, yeah, blah blah. Okay. So I think what I can do. Let me search again. Okay, let me just use this reference here. So we need to have a toggle pin that we can pull this boot 0 high or low. So by default we should put it in one of these modes, right? So I'm gonna copy that and bring it over here, boot 0, like that, right? Boot 0. Okay, Next is reset. Reset is just like a toggle, it's like a push button that you can press to just reset the whole program. So this is a general schematic that I use. Obviously 10 kilo ohms and 100 NF RC. There are like stuff associated with the timings and whatever, not RC circuits here, but you know, it doesn't matter, it works anyway. But for high-end designs, you need to check everything. So if this reset time is gonna cause delays and etc, you better check it, right? So, and reset is right here. I think I can rotate that, but no, I think I can just put it right here and label it. So this is connected to that, this to that. We put ground somewhere here, put ground. Okay, so we connect this other end of the switch with ground, and we label this part right here. We call it and reset. Oop. Yep, and reset. Where is that? This one. And RST. Okay, so this is connected to 3v3. This is an RSC. An RST is connected to this pin. Right, cool. So when you press resets, right? Let me put it where? Let me put it here. I think I should delete this and just organize this a little bit. And we're gonna have, this is boot 0. Boot 0. Okay, let's connect this to boot 0 also. Right there, cool. Anyways, yeah, so that's fine, okay, so let's check what we have here. Let's look for system call, reset and clock controller, high speed external, enable crystal. Right, so this is pH0 and pH1. Let's confirm with the data sheet again. pH0. Yep, where is the table for that? Yeah, oscillator in pH0. So come back to the EZDA and we put pH0 is somewhere here. So we put, I'll shorten this guy to OSC in and OSC out. So yeah, I think I forgot to like go through the system requirements for this payload, because you know, like systems engineering just says normally that you have to define what your system is supposed to do first before you go to the details. So it's a top-down approach basically, especially for these systems. You want to change if you come up with system requirements and then design for iterations, you don't want to be changing the system requirements, you want to be changing the design, because there are a lot of constraints in a CubeSat. For example, let's say that your center of mass, your weight stuff, your, let's say you know, radiation capability, power has failed maybe to turn out the way you wanted. You change the design, not the system requirements, right? So I think I'll go through that at the end of this video. It's almost done with this part 1, but I'm going to put part 2 later. Oscillator in is pH0 and oscillator out is pH1. So put it right there, rename this out. Okay, cool. So let me minimize this. All right, This thing has audio. Okay. What's next? Next is so we have the power, we have clock, we have we don't have programmer, we have the boot and reset. Let's put the UART debug. So come back here, go to the connectivity, UART. It has a lot of UART. UART 1, for example, synchronous. Let's look what pins are those. So this is UART P9 and P10. P9 is TX, P9 is TX. So come back here, I copy the pin header that I have. I can debug this board from the OBC2, but we can get away with this one. Probably I'll put like right-angled pin headers so that it does not like disturb the mechanical mount of the payload, because the camera should lie flush on the surface, should not protrude out of the CubeSat surface, so that you maintain the dimensions and the pod deploying pod dimensions requirements, right? So I'm gonna take this connector, is it UART right here, copy, bring it back here, paste P9 and P10 right here. So let me put that there, or I can also put it right somewhere. Let's see, maybe there. The schematic is small for some reason. Let me change the page size to A3. Confirm. A3. Okay. Yeah, that's better. So I have a little bit more space. Okay, so just put this somewhere. Oops. Somewhere here. Boot. Debug RX is P10, right? So we're gonna put that P10 right here. And then I'm gonna connect that there. Then we put TX right there. Wire these two. Okay, cool. So UART debug is handled. You know, there are some things you can put like 22 ohm resistors, etc for spikes on the RX-TX line, but for now that's not necessary yet. Next is SWD for programming. So SWD is, where is it? It is right here. But what I'm gonna do, let me show you. I'm gonna I just put it a placeholder. Let me put it there. Come back to CubeID, go to System Core Debug, System Debug, serial wire, sorry. So PA13 and PA14, these are pretty standard across all MCUs for STM32. PA13 is SWDIO, data in out. PA13, where is it? It's right here. PA13. The other one is PA14. P14 is up here. So we're gonna put P14 is clock. This is WCLK. This other one is SWDIO, right? Save and update this other side. What's wrong with this thing? Keep resetting. Okay, so this is gonna be named SWIO, and this is gonna be named SW clock. I need to check that. Cool. So yeah, so that's fine, but I'm not gonna place this on the schematic on the PCB, right? So this one property, I don't want it in the BOM, I don't want it there. So again, as I said, I'm gonna program this board from the OBC. So I need to finish the design here and then see how many pins, connector pins, I need to jump to the OBC. Okay, so let's add an LED, a basic LED. Let's say green. Do we have a red one? Green is fine. Okay, green is totally fine. Paste that. Let me put it where? Let me put it right here. The schematic is like dirty, very dirty. Sorry. Oops. What happened? Okay, so I'm gonna copy this and let's say put it, use LED green. Use LED green, put it, oops. Use LED, oh, okay, I'll change that later. So which pin do we want that to be? We can use any pin for now, but I don't know. Let's use PC13, GPIO output, right click, enter user label, user LED. So that's PC13. Where's PC13? It's right here. PC13. Wire that, connect it here, and yeah, we're good. We are good to go. Let's do that. Okay. So what's remaining is what we have, this, that. Okay, so I think if you power and program this board, you should be able to like blink it, if I'm not wrong. Yes, you should be able to like blink that LED on the PC13 pin. I hope there's something I've not forgotten. Of VCAP. Yeah, there is this VCAP. VCAP is like an essential part for this STM. So VCAP, there's VCAP 1 and VCAP 2, but this one has VCAP 1 only. I think I've not added some decoupling stuff, but I will do that probably the next video. But let's check about this VCAP lastly and move on, rather than end this video so that it doesn't become too long. There is a capacitor that should be connected to VCAP. Let me check that real quick. Yeah, VCAP 1 and VCAP 2 external capacitor. Stabilization of the mains regulator is achieved by connecting an external CXT to that. CXT is specified in table 16, which is right here. So SCR and ESR and capacitance is down there, and bypassing the voltage regulator, 2.2 capacitors are not required and should be replaced by 200 NF anyway. So I need 2.2 NF, 2.2 UF microfarads, 2.2 UF. Do I have it? I don't have it, so it means I have to search it back here. C0805 2.2 UF. Yep. We need to check the ESR also, but maybe I'll check that. copy this, Shift F, paste, and place. So bring it down here to pick up. Let me close this guy. I'm just gonna bypass this, avoid crisscrossing lines, but I am doing it. I don't know why I'm telling you to avoid it, but I think there's no other. Obviously there's a better way to place this, maybe there. I think, yep, that should be cool. Right, so this is it. Took us 42 minutes to design this very basic thing, which is like super slow, but well, at least we have the MCU working. And next video, next part 2 of this payload, we are going to add now the FSMC, the DCMI, and the connector to this board. It's a pretty basic board for that case, because it has very few components, etc. Right, so yeah, that's it about this video, and I'm gonna see you in the next one. All the best. I'm gonna leave the link to all the design block diagrams, etc, and readme on the GitHub. I'm gonna leave it in the description, and yeah, all the best. Bye bye.